There we go. Hi, everybody. Welcome back to Chem 121. We're almost done with the quarter. It is now week 9, and there's this week, there's next week, there's an exam after the end of week 10, which will get posted on, like, Thursday or Friday. And there's a cat. Hi, yes, I'm working. Yes. Okay. I lost my train of thought because of Maya. We have finals week. There's a final coming up after exam number 2. So yeah, we're almost there. I think this is the slide we left off on last time. I'm pretty sure. But what I wanted to do is give everybody like 5 or 6 minutes to do these problems if you haven't done them already. If you did, you already have the answers written down. You can just type them in real quick. But go ahead and answer these 3 questions. Top one is a mass percent. The middle one's a mass volume percent. The bottom one is a molarity. So go ahead and do these. We'll go over the answers in about 5 or 6 minutes. Or after I tend to this cat. Yeah, say hi. Or you can just rub the mic. That works too. Say hi. Hello. Hello. Let's do 1 or 2 more minutes, and then we'll go over the answer to these problems. Say hi. Hi. Maya. Maya. Yeah. Now, I'm trying to get her to talk, and she just wants to jump on my lap. Don't you? Say hi. Nah, she's just not chatty today. All right, so let's go over the answers here. For some reason that didn't show up. There we go. She's just gonna chirp in my ear. That's what she's gonna do. All right, what is the mass percentage of silver nitrate in a solution made from these components? So we know that mass percentage is the mass of the solute over the mass of the solution times 100%. And so that's going to be, what's the solute? That's the stuff that we dissolve into our water. That's going to be that many grams of silver nitrate. That's our solute. And we're going to divide that by the mass of the solution. So that's both things added together. So 30 plus 2.13 would be 32.13. Times 100%. We'll go over the calculator here, which is hiding for some reason from me. Oh, not divide by 100 times 100. So we get 6.63%. All right, so this solution is 6.63% silver nitrate by mass. All right, we got the other solution here. We can do sodium nitrate, and I want the mass volume percent. So remember that mass volume percent requires you to input units in certain things. So the mass of the solute needs to be in grams, and then the volume needs to be in milliliters for the entire solution. And I forgot times 100, because it is a percent. And so that would be, so I got 100 grams divided by 1,250 milliliters. And let's see what we get. So 100 divided by 1250 times 100 is 8%. And that is NaNO3 MV. And then finally, we have molarity. So we'll need to figure out some moles here to do this one. So that would be molarity is moles of solute over the volume of the solution, that's in liters. And so the moles of the solute is going to be this calculation here. We'll do it in blue. So I've got 25 grams of sugar or glucose. And remember, from chapter 6, we could turn grams of something into moles. I can hear the cupboards in the kitchen opening and closing because my cat is hiding in them now. Oh my goodness, Maya, you're so weird. How many grams per mole is C6H12O6? Well, we can go to Lentech and calculate that. So we'll put Lentech on the screen here. See if I... Yeah, that's good enough. And we'll just type it in. C6H12O6. You can see over there in the common organic compounds right here, it's telling us what this is because this is common enough. And 180.16 grams per mole, so we'll write that down. All right, so how many moles is this? So 25 divided by 180.16. So it's that many moles. 0.139. All right, so that's the number of moles of solute there. And I can divide by the liters of the solution. So I'll just write that in. So 0.139 moles of... Uh-oh. There we go. Of glucose divided by the volume of the solution. And so we just go like this. And I get a 0.0925 molar solution. Oops. Which we'll just do like this. There you go. All right, that's how we express concentration mathematically. Just to review what we did last week, let me know if you have any questions. All right, there's the homework practice for this section. We're going to do one more mathematical thing. Oops, I didn't mean to skip past it. And then the last two sections we could just breeze right through because they'll be basically just properties of matter that we can discuss. And then we'll start chapter 9. So we'll get chapter 8 done today. And chapter 9 is pretty short. So, all right, so now that you know how to express concentration, a thing that you can do is dilute solutions to a lesser concentration by adding water. Now, in general, you're just going to add whatever the solvent is, but since we're working with aqueous solutions anyway, I'm just going to say we're going to add water. So, and the way that this works is that if I have a solution that's concentrated, oops, I want to draw on the solution. So let's suppose you have Kool-Aid. You may have done this with Kool-Aid where you have like very little of it left and you add some water. So if this is your Kool-Aid pitcher, oh yeah, there he is. It's even got the eyes on it. That's just kind of creepy, actually, but that's okay. So let's suppose that you have a pitcher of a liquid. And for the purpose of this, we're just going to call it Kool-Aid. So if you have a little bit of Kool-Aid down here and it's really, really dark and intense in its red color, you could say that it's concentrated. Now, if you add H2O to it, because maybe you just don't have enough Kool-Aid, and you want to have more for the kids, but you didn't buy any at the store. I don't know. If you do this, then what ends up happening is that the color of the Kool-Aid is much fainter than it was before. And that's because you diluted it. So when you add water to something, you dilute it. Whatever is in there is the same amount, but now it is in a bigger volume. Pretty much all, like, juices and stuff that are from concentrate operate by this principle. So if you buy, like, the lemonade or limeade or orange juice or whatever in those little tiny frozen cylinders that you get in the freezer aisle, if you try drinking those on their own after they have thawed out, they're just way too sweet. Because it's just pure concentrated orange. So you add water to it. And you add as much water as you want. In the medical profession, dilution is necessary because we're going to be wanting to make IV bags for saline solution all the time. But shipping around water is expensive because water's heavy, right? However, water is relatively abundant. You could just add water wherever you are. So if we just ship you something very, very concentrated, or even just the salt, and then you keep a concentrated solution in storage, you could just take portions of that, and then make the solution to whatever concentration you need. For diluting solutions, we're going to use this formula. So the formula is CSVS equals CDVD. So what does this mean? So we're going to draw a line down the center here. S is the stock side of the equation, or in other words, what you have already in the stockroom. Or your supply room, or whatever. D is the dilute side. And you want to prepare the dilute stuff. It doesn't exist yet. Now, for each of these sides, you have a C term and a V term. So the C is going to be the concentration of your solution, and the V is going to be the volume that is used. Now, for the volume term, on the stock side of the equation, the volume used is going to be something you calculate and then determine. But on the dilute side, we're going to change that a little bit. On the dilute side, you're going to select a volume that you wish to prepare. You're also going to select a concentration to prepare. In other words, you're going to select these. You get to pick whatever numbers you want to do the dilution. Maybe you want 1 liter of 0.9% mass volume sodium chloride. Maybe you want 20 liters of 0.5 mass sodium chloride. You put whatever numbers you want in there. Generally speaking, this number is going to be fixed. Which leaves the volume of the stock solution to be the number that we solve for most of the time. If we are doing a solution preparation procedure, you're going to solve for the volume used. The volume that's used is going to tell you how much you're going to put into a flask, and then the concentration and volume of the dilute solution will tell you what to do from there. So let's look at some example problems, and we'll see this in action. All right. So the first question we're going to do is, I need 100 milliliters of 0.05 molar HCl. All I have, though, is 4 molar HCl, and that's way too strong. That will just dissolve whatever substrate I'm using immediately, and my reaction will be over before I can even record the data, or something. How do I dilute the solution? So let's do that. Let's capture the problem real quick. All right, so just like before when I had like P1V1 equals P2V2, I'm going to do something like this. We're going to make a little table. We're going to fill in all the numbers that we have. So the first sentence says, this is the solution that is required. I need these things. But the stock room has this thing. Well, we know that the stock room is going to be S, and we know the concentration because it's written as molarity. So I will write 4 molar HCl as my stock concentration. Now, the diluted concentration must be the other molarity. So that would be 0.0500 HCl. How much of this do I want? I want 100 milliliters. All right. This is the variable that's left over, so I'm going to solve for that. So when I write my dilution formula, we're going to solve for this one. And then we just fill in the numbers. So CD was 0.0500. The dilute volume was 100 milliliters. And the stock concentration was 4 moles per liter. Now you'll notice that the units just go whoop, they just cancel right out. And that the units of volume that I get will be whatever units I left in the expression. So these volumes can be any units you want to, as long as they are the same. And the same is true for the concentration. You can use any concentration unit you want. So you can do mass percent, you can do mass volume percent, you can do molarity. Doesn't matter, as long as they are identical. Because the whole point is we want our units to be able to cancel out so that we can use the units of the leftover thing for our answer. So, whatever number I get from this calculation is going to be my answer in milliliters. And I got 1.25 milliliters. Okay. Now that I know what the stock concentration is, I need to dilute the solution. So how do I describe how to do that? Well, first let's draw a picture. And then we'll show a preparation for this. So I'm going to have a flask. And I don't know what happened to the bottom there. Drawing a flask is difficult. There we go. And my flask has a fill line on it. And this fill line is for 100 milliliters. So I want 100 milliliters of my solution when I'm done. My dilute solution is going to be in this flask. So what I'm going to do is I'm going to add I'm going to add 1.25 milliliters of the concentrated solution, or the stock. Well, I should write as stock, actually. Because concentrated actually means something different in a different context. So I'm going to do that, and that's going to look like this. So in it goes, and acids aren't blue, so let's make them We'll do pink, I guess. All right, so there we go. I've added my 1.25 milliliters. It looks very concentrated, because it is. Then step 2, we're going to add enough H2O to reach this fill line, because if I had 100 milliliters, I would end up here, right? That's no good. I don't want to end up above the 100 milliliter mark. So what I need to do is add enough water to get this volume up to here. And it should look like that. Now, if this is all water and the HCl just kind of settles to the bottom because I haven't mixed it really well, the last step that I would need to do would be to mix it really well. And the way that I recommend to do that is to just mix it for 1 minute. So put a lid on the top, flip it upside down, flip it right side up, and then just keep doing that over and over and over again for about 60 seconds. And what will end up happening is that all this pink that was down here before, which was our concentrated acid, will now be equally distributed through the solution. And when it does that, its concentration will equal the amount that we calculated earlier. Not to mention, its volume is the volume that we dictated when we prepared the solution. So those are the 3 steps to making a solution. The first step is to add whatever you calculated. Step 2 is to add water to the fill mark. Step 3 is to mix real well. Do that for about a minute. There is one last step. Enjoy. Enjoy is optional. Maybe you don't enjoy making solutions. Maybe you don't enjoy HCl. You should not enjoy HCl, but... Alright, so this is again what we just did. There's our stock solution. There you go. So now what I want you to do is I want you to use the same 4 molar solution that I used in my example, and I want you to make these solutions. So you're doing 3 separate problems here. I want you to make 25 milliliters of 1 molar HCl, 250 milliliters of 2 molar HCl, and 1,000 milliliters of 0.0250 molar HCl. More or less exactly what you've been doing for the formulas with the earlier, but we're going to be just applying this different formula. Solve for the thing you need, and then follow this procedure that I outlined over here. Your numbers will just be different, but the procedure is almost exactly identical. All right, I'll give you like 5 or 6 minutes. We'll go over the answers at that time. 1 or 2 more minutes and we'll go over the answers. All right, let's go over these solutions. All right, so we're going to do more or less the same problem here that you can see on the screen. I'm going to do it fresh each time. So for the first solution, we need to have, so we'll go like this. So there you go. So concentration of our stock solution will always be 4 molar HCl. Now for the first problem, I want to make 1 molar HCl, and I want 25 milliliters of it. So I'm going to solve for this. There we go. And then we'll just plug in all the numbers. So the dilute concentration was 1 mole per liter. The dilute volume was 25 milliliters. And then the stock was 4 moles per liter. And those cancel out. And so this would be, I think it's 6.25. Yeah. All right. So for solution number 1, to prepare this, for step 1, we would add the concentrated solution, the amount that we calculated, to a flask, and the flask needs to be whatever volume our dilute solution would be. So that's this right here. And then steps 2 and 3 are going to be the same each time. So add H2O to the fill line, and then mix for 1 minute. And enjoy. All right, so that was the first problem. Now for the second problem, we're going to just go back up here, and then I'm going to overwrite stuff in pink that changed. So That's going to be this. So I need 250 milliliters this time. And I want 2 molar HCl. So we're just going to plug in different numbers. And that's these numbers right here. So I have my dilute concentration is 2 molar, and I wanted 250 milliliters this time. So 2 times 250 divided by 4. And so the only changes that you make when you make your procedure down here are... Oops, that one actually stays the same. So I want to add the amount that I solved for, and my flask is now this volume because I'm making more solution. And everything else is the same. Now, when you do the calculation for 1,000 milliliters and 0.0250, that table's going to look like this. We're going to just save some time here. We'll fill in the table. So I need 1,000 milliliters. And I need that molarity. So when you do this calculation, you're going to get 0.0250 times 1,000 divided by 4. And you actually get the same answer that you got for the first one. And you do the exact same process. VS is your 6.25. That's the amount of stock solution that you're going to add to the flask. The flask is 1,000 milliliters this time. Fill that with water. Mix for a minute. Enjoy. So, same idea. All right. We're going to take a break, because that's about at the time that we are at for now. When we come back, we're going to talk about colligative properties, which is going to involve a bunch of stuff that we do in the winter with salt. Is really how I introduce colligative properties. So we'll see you for that in about 10 minutes. I know it's going to pop up. There it is. Okay. So we'll start this, and we'll get some music going. So see you in a bit. Oops. I was sitting there listening to the music. There we go. On the screen is the homework practice, just in case you didn't get that. Let's keep going. So, the next section we're going to talk about is colligative properties. In the winter, I like to ask the question, why do we put salt on the road? And that's a question that's kind of like, well, it melts the ice. Duh. But then my question would be, okay, well, how does that work? And that's what we're going to talk about here. So, colligative properties are properties of solutions that occur when you add a solute to them, but it doesn't matter what the solute is. So we're not actually doing chemistry. What we're doing is physics. And we're going to see this in action right here. Now, the only thing that matters for a colligative property is how much of the solute you put in there. So we're going to be putting things like sodium chloride, sugar, antifreeze, these sorts of things. There are 4 specific properties that we're going to care about, and those are these right here. Now, several of these are linked together, and one of them we're going to talk about in its own section. So we're going to talk about osmosis and osmotic pressure, because that's probably the one that's most relevant to you as a nursing student. All right, so let's talk about how particles behave in solution and can cause inhibition to any of these properties here. Well, first let's say what the properties are. So the first property we're going to talk about is vapor pressure lowering. In other words, if I have a solution and my liquid can evaporate, it would form a vapor pressure. By adding in solute, that's going to make this number decrease. That's interesting. How does that happen? Well, we'll show. It's actually really obvious why it happens. Boiling point elevation and freezing point depression are going to be extensions of this one. More so boiling point elevation. Freezing point depression sort of occurs for a similar reason, but it's not directly related to the vapor pressure. And then again, we'll talk about osmotic pressure in just a little bit. Now, the number of particles that you have is going to affect this. So if I have lots of particles versus not very many particles in my solution, we're going to have stronger colligative effects in the concentrated solution as opposed to the dilute solution. Sorry, I had to hit mute there so I could cough. I'm still congested. Now, if I have more particles, there are stronger colligative effects, but I don't necessarily have to have more concentrated solution. I just need more particles, because remember, the particles are the only thing that affect it, not the identity of the substance. So, for instance, if I have glucose, glucose is a covalent compound or molecular compound. And what that means is that it does not dissociate. Or in other words, it doesn't split into ions. So if you put sugar as glucose into your solution, you're going to get a bunch of little individual glucose molecules. And they'll all have the formula C6H12O6. So we would say, okay, glucose contributes 1 molecule per glucose. And it's itself. Now, what if we instead used sodium chloride? Well, sodium chloride is ionic, and ionic compounds dissociate into ions. So sodium chloride would dissociate into a sodium ion and a chloride ion. And so for each sodium chloride, quote-unquote, molecule, formula unit, we'll call it, you actually contribute 2 particles. And so using sodium chloride would be twice as effective as using sugar. Now, from the perspective of which of these will freeze our road more effectively, sugar is sticky and gross. We don't want to spray sugar all over the road, right? That'd be gross. You step out of the car, and you don't slip and fall because you're physically stuck to the ground. I mean, that's a solution, I guess, right? But sodium chloride is very effective at doing this because it makes twice as many particles, and also it doesn't stick to your boots. All right, so based on our descriptions here, we've got CO2 and KBr. One's molecular, one's ionic. I want you to type in the chat, which do you think will be more effective at creating our so-called colligative properties here? Type your answer in the chat. We'll check it out in just a second. All right. KBr is correct, because KBr splits into two particles. CO2 is molecular, it just stays CO2. What about this one? Which one splits into more particles, CaCl2 or sodium phosphate here, Na3PO4? All right. Correct answer is indeed Na3PO4. Because Na3PO4 splits into 4 separate particles. We've got our NAs. They're all positive here. We got our phosphate. So this would be a total of... That was supposed to be a little curly bracket, but... 4 particles there. But for calcium chloride, I have a calcium, and I have 2 chlorides. And this is only 3 particles. Now that might make you think, well, why don't we just spray sodium phosphate everywhere if it's 4 times as effective? And the answer is, well, phosphates can be reactive. Phosphates are parts of fertilizer, and we already know that runoff from fertilizer going into drinking water, not necessarily a great thing. So, there are reasons why we would not pick simply the molecule that has the most dissociation. All right. Now, why do colligative effects happen in solutions with these substances? So, first, let's look at vapor pressure lowering. If I have a solute, now the word non-volatile here just means does not evaporate. If I have a solute that I add to a solvent, the vapor pressure of my solution goes down. So you can see up here that I have some number of particles that generate a pressure. But by adding my solute, mysteriously, I have fewer particles. Why is this? So what we're going to do is we're going to draw a picture. Here's the side view of my solution. My solution has solute in it, which I'm going to represent by these red circles that I'm drawing. Now, if my solution is randomly dispersed, so let's say I have 20% of the solution is solute, then that means that 20% of molecules in here would be solute. Now, if I'm randomly putting my molecules in here, they're going to randomly occupy spots all over the place, and that's going to include the surface, right? Well, if the surface is covered 20% by my solute, then where I have my solvent, which is water in this case, if water wants to evaporate, it can only do so where it has access to the surface, right? It cannot do that where there are solute particles because they're physically obstructed. And the end result is that, well, less molecules just make it to the vapor phase because the surface is covered partially by solute. If you could cover it 100% of the way, nothing would get through, right? If you cover it 50% of the way, half of it would go through, and so on. So if you wanted to calculate the vapor pressure, you could, but we'll leave that to engineering. All we really care about is that the vapor pressure of a solution decreases when you add solutes to it. All right, now if vapor pressure goes down, that means that you have to heat something up even hotter to get enough vapor pressure for it to boil. Because remember that boiling occurs when the vapor pressure equals atmospheric pressure. Well, if it's lowered because I have a solute in there, that must mean that the boiling point temperature must increase with solute in there. And this is entirely the point of putting something like antifreeze into your radiator to prevent your engine from overheating. Now, it's called antifreeze because primarily it's used to prevent freezing. But an additional effect of this is that when you add something to your radiator, the boiling point of the water that's inside the radiator in your car engine will increase, and thus it can absorb more heat from the engine and resist overheating. And the story I like to tell everybody is that apparently, when I was a kid, we would go camping with another family, and they didn't understand this principle that antifreeze would cause the boiling point of the water in the radiator to increase. Because what would always happen is we would drive up to the mountains to go camping, and that would be like a 5,000-foot elevation change. Their truck was really, really, really old and towing a really heavy trailer, and so the engine would overheat every single time. And it would oftentimes overheat multiple times. So we'd almost be there after like 4 or 5 hours, and we'd have to sit on the side of the road for an extra 1 or 2 hours because they didn't have any fucking antifreeze. Ugh. I had a shitty childhood. And the reason for that was because nobody understood chemistry. So better living through chemistry. Spare your children the heartache of sitting on the side of a highway on a mountain where it's so hot. Or, do whatever you want to. I mean, camping should be fun, right? That part just wasn't fun for me. All right. Let's talk about how a freezing point is reduced by adding a solute to it. Now, in picture A, we can see the freezing process graphically. So molecules of water will bounce around randomly in the liquid phase, but to freeze, they have to align themselves up into a nice little solid. This is so that they can maximize intermolecular forces and the attraction from them. That will lock them into the solid state. But if you add a solute, the solute inhibits the ability of the molecules to do that. And you can see that the freezing over here on picture B is very disorganized. In order for my molecule to freeze, I have to get it to be ordered in the solid state. I have to have my molecules close together. They have to be attracted to each other. The solute gets in the way. And the only way for me to fix this problem and to actually freeze something is to just lower the temperature even further. The result is that when you add stuff to your liquid, the freezing point decreases. Now, as true to the antifreeze name, this is why you put antifreeze in your car. When the water in your radiator tries to freeze, the antifreeze molecules inhibit that, and you have to get it colder and colder to do that. Now, you might not necessarily care that water is freezing in your car if you're going to turn it on, but when water freezes, it expands, and that's not great for an engine block. That's how it cracks, and that's obviously very, very bad. Sorry, more coughing. I apparently decided to catch a cold in the middle of summer. Because That's a thing I wanted to do. It's not COVID, thankfully. All right. So those are our 3 colligative properties besides osmosis, which we'll talk about in a second here. I'm coughing again. Sorry about that. All right, so let's move on to osmosis. Osmosis is the 4th colligative property. And what osmosis basically is the ability of water to move through a semi-permeable membrane. You're probably aware of this because at this point you've either done the lab or at least looked at it. The lab for this week that's due on Wednesday, I believe, talks a little bit about osmosis. So we already understand what osmosis is from the video, but let's just go over this real quick anyway. We're going to define certain barriers in biology as semi-permeable. What that means is that if I have a barrier that we're going to identify as semi-permeable, only certain stuff can go through it. Now, in this case, we're going to allow water to go through this semi-permeable membrane because water is a tiny molecule. So if a barrier has like pores or holes in it or something like that, and those pores are of a certain size, only molecules that are smaller than that size can fit through. Any molecules that are too big or have certain properties that get repelled or interrupted by the barrier can't go through it. So in this example here, these green molecules are the ions in our solution. The ions are too big, so they just bonk off of the semi-permeable membrane, and they stay on their side. Water, however, can go in any direction it wants to. Okay, what are the effects of this? Why do we care about this? Well, in biology, it's very important to keep stuff in certain places. For instance, if the contents of your cells all pass through your cell membranes and entered your bloodstream, you'd very quickly die because you're not supposed to have proteins in your bloodstream that shouldn't be there. That sort of stuff is transcripted in, I don't know biology. Endoplasmic reticulum, I think, is where you do this. I don't remember. Mitochondria is the powerhouse of the cell. Everybody knows that one. But yeah, so you want to keep certain things on certain sides of your semi-permeable membrane. Certain other things you want to be able to go in and out freely, and there are structures and specific barriers that are allowed to do that. Now, if you have a different concentration of ions on one side of the barrier relative to the other, then an interesting phenomenon happens, and that phenomenon is what we call osmosis. What is going to happen is this. Our solvent will move through the barrier with the intent to make the concentration on both sides equal. In other words, what's happening is very slow mixing. And I'm going to put that in quotes, because it's not actually mixing. But the water is trying to move in such a way so that the solution is effectively mixed. Now, if you have ever made a, I don't know, food coloring in water, for example, you drop like 2 drops in, and the food coloring is very thick and dark where the drops enter the water, and then it like slowly permeates out. And then eventually it will fill the entire thing, right? So let me find a picture of that. So something like, yeah, this. Here we go. So let me get this on the screen here. So if you add food coloring to water, it looks kind of like this, right? Now, initially that's what it looks like, but eventually when it's done, it will fill the entire thing. And they don't actually have a picture of it when it's done. But you can see in this picture right here, it's more or less filled the bottom. And eventually it will fill in all of the entirety of this, and it'll all be one color. So it'll all be evenly mixed. Mixing occurs on its own because molecules are moving randomly. So all solutions will try to mix themselves, essentially. With osmosis, a barrier is in the way, but water can move through the barrier anyway. It's just the solute can't. And so the water is going to move in the direction so that the solution becomes effectively evenly mixed. And the way that the solution thinks that that has happened is that the concentration on both sides is the same. Now, some interesting things will happen when this occurs. For instance, let's suppose that this is what my solutions look like. I have this tube here that is bent upwards so that it's in the letter U. That would make it a U tube, wouldn't it? On the left, I have a concentrated solution. So there are more ions on this side of the solution. On the right, I have a dilute solution. I'm going to redraw this. So here's my semi-permeable membrane in the middle here. And I'm going to have a really concentrated solution on the left here, and a not very concentrated solution on the right. Let's suppose that my water moves in this direction. If that were the case, I would have more water on the left than the right, so the volume would go up in the volume on that side, and the volume would go down on that side. Well, if concentration can be expressed like this, or in other words, how many particles there are divided by the volume, if I make the volume go up, I'm dividing by a bigger number, and therefore the concentration would go down. Likewise, for the other side, if the volume is reduced, the concentration goes up. Well, if the high side is decreasing and the low side is increasing, eventually those will have the same concentration. In other words, they will be evenly mixed. And so this is what osmosis is. Water will move in this direction so that the concentrations eventually end up being the same. And you actually create a little column of water when you do this. The water will push itself against gravity, if it needs to, or against other forces, to mix the solution thoroughly. Now, if the concentration difference is too big, water can't push or support itself that much. And so you won't perfectly mix the solution, but you will have a very high pressure from osmosis occurring, and so that's called osmotic pressure. So this column of water here would be our osmotic pressure. Or in other words, the pressure exerted simply by the force of osmosis occurring. And that pressure would be exerted in all directions. Now, can you think of an analogy for a pressure that could happen in biology? For example, your body. I'll give you a hint. It has the word pressure in it. It may be increasing because of this class. That's right, it's blood pressure. Blood pressure is basically osmosis in action. Having too high of a blood pressure is bad because that means that there's a lot of force on your arteries, on the cells in the arteries, etc. But having a blood pressure that's too low is also bad too. We're going to talk about that a little bit when we look at blood cells, not molecules, in just a second. So osmotic pressure is the pressure that is applied against osmosis. It stops it essentially from happening. Osmosis itself exerts a pressure because it's a force going in a certain direction. The counter to that we call osmotic pressure. Now, cells are very, very susceptible to osmotic pressure. If you have a cell membrane and it's subject to a lot of pressure, then the cell can crumple inward and collapse. Likewise, if the cell pressure from the outside is too low, then on the inside it will push outward and the cell can explode or rupture. Neither of those are very good. And we're going to talk about how these occur. Now, because the amount of solute affects the concentration of the solutions and thus how much water moves through a barrier, osmotic pressure must be a colligative property. The more salt there is, the higher the concentration, the more the solution is affected in terms of osmosis. Let's look at two ways that this can be detrimental to the health of your cells. We're going to come back to this formula in just a second. Here's the first case. Let's suppose that I have lots of ions outside here. I'm going to just draw pluses, even though there should be minuses. There we go. And inside my cell, I just don't have that many. What the cell's going to do is it's going to say, oh, okay, I need to equalize the concentration. I need to move water in the direction of where there are more ions so that I can dilute them, thus concentrating where there are fewer ions. So here, water is going to leave our cell to try and dilute the surroundings. This process is called crenation. Basically, what happens is the cell shrivels and cannot perform its intended function, and it could possibly die. Now, when would this happen? This happens if you eat too much salt, or if you're in the ocean and you drink salt water. In any case, you end up with a concentration of ions in your bloodstream that's too high, and you cause dehydration. Now, the solution outside the cell, too many ions, so we use the term hyper, as in too many, tonic. So a hypertonic solution causes crenation. Moral of the story, don't eat too much salt or drink salt water. Your blood pressure will go up. And that makes sense, right? What's the first thing they tell you to cut from your diet if your blood pressure is too high? They tell you to eat less salt. This is why. Now, what happens if you have a blood pressure that's too low? How does this happen? What ends up happening here is that if you have very few ions outside the solution, but relative to the inside you have lots of ions, or relative to the inside the inside has lots of ions, then the opposite process occurs. So this will occur if you overhydrate. So if you drink too much water, then you dilute the amount of ions that are in your blood. And in this case, water moves it moves in the same direction from low concentration to high. It wants to dilute where there are too many ions to get equal mixing. In this case, the cell gets too big. It fills with water, it inflates like a little balloon, and then... I don't know if it caught that. Let me try that again. There we go. Yeah, you do not want your cells to go, that's bad. That's very bad. This process is called hemolysis, and hemolysis occurs when you have a hypotonic solution. Hypo meaning too little. Now, by the Goldilocks principle, there must be some concentration of ions that is just right. And there is, and that's called isotonic. An isotonic solution has the same concentration of ions both inside your cells and outside your cells. Now, Professor West, what is that concentration? How would I know what concentration of solution to make if I wanted to treat somebody for dehydration? And the answer is, well, scientists have figured that out. It's this. This is your saline solution. This slide is probably the most relevant thing to nursing in this entire class. Saline solution is isotonic with blood if the amount of saline in the solution is 0.9% mass per volume. In other words, if you wanted to make this solution, you would need this many grams of sodium chloride per this many milliliters of water. Because the hundreds here would cancel out, and you'd get a 0.9% NaCl. Now, this is for dehydration. If you have malnutrition, for example, if somebody is lost in the wilderness and they have not eaten for days, you can't just give them saline solution. That'll rehydrate them, but they need sustenance. If you need a glucose solution to do the same thing, we can calculate that out, and this is the percentage you get. For glucose, it's 5% mass volume, because glucose is a bigger molecule. It's heavier, and it doesn't split into two pieces. Sodium chloride will split into two pieces, because remember, all ionic compounds will dissociate, and we have colligative properties depending on the number of pieces that happen. So, these two solutions are very relevant to you if you are working in emergency care. Now I'm going to go back a few slides here. We're going to go back to the formula that I just skipped. You can see that we're on the last slide here. Where is it? There it is, osmolarity. What we're going to do is we're going to assign a number to a solution so that we know which solutions have the same osmotic impact, basically. And so this is called osmolarity. And what osmolarity does is if you have two different solutions that have the same osmolarity, they will have the same influence on osmotic pressure. In other words, that 9%, not 9%, sorry, that would be way too concentrated. That 0.9% sodium chloride solution has the same osmolarity as the 5% glucose solution. Now, those numbers aren't at all the same, but remember, it's because we're dealing with molarity for osmolarity, not MV%. That's not molarity. So, if you know the molarity of a solution, you can multiply it by this term right here, I. I is the number of pieces or particles a substance dissociates into. For example, if I was looking at sodium chloride, I would be 2. But if I was looking at carbon dioxide, I would be 1. So this is where the influence of the number of pieces or particles something will split into affects osmotic pressure. If it splits into 2, it's twice as effective. So let's look at an example of calculating the osmolarity of a solution. What would the osmolarity of a 1.50 let me try that again. 1.50 molar sodium chloride solution be? Well, the molarity is 0.1 or 1.50. We're going to multiply that by the number of pieces sodium chloride splits into. And what we write is we write this. So this solution would have an osmolarity of 3. And it would have the same osmotic effect as a 3 molar solution of, say, glucose. That did not dissociate in any pieces. So glucose would have I equals 1. And both of these would have the same osmotic pressure. Because they have the same osmolarity. So you can calculate osmolarity and then use it as a reference to compare stuff if you know the molarity of the original stuff. Now, in healthcare, we've already done that for you. And if you look really carefully on a bag, let me look at an IV bag. So IV bag, fine print. Let's see if we can. I typed in fine print and I got a bunch of pictures of like wall art that you would put on, and they're all IV bags. So IV bag. Trying to find one that is big enough that it actually says the Osmo. So I actually have one of these on my desk at work for this reason. I bring it to class for this lecture. I don't want to order it. I just want to read the damn numbers. Oh, that was almost what I wanted. Oh, you can barely read it. Okay, well, let's see if I can do this, but... Okay, so I found a place where you can order saline. If I do... Oh, it does zoom in. Okay. I don't know if you can read it here. I have to have my cursor in a very specific spot. But it says each 100 milliliters contains 900 milligrams sodium chloride, pH 4.5 to 7. Then this says sodium 154 milliequivalents per liter, chloride 154 milliequivalents per liter, osmolarity 308 milliosmol per liter, calculated. So the osmolarity of the solution is 0.308, in other words. And if you have any other solution that has that osmolarity, it would be isotonic with your bloodstream. So there you go. That's just a sort of fun thing that you can do. All right, so let's go back over here. So we'll put the homework practice on the board here, but basically these numbers are your targets if you're going to hydrate somebody. So let's suppose that you wanted to administer these solutions to, like, say, a sample of blood to observe their effects. So, like, this isn't somebody that you're giving these solutions to. You just have blood that you're going to, I don't know, rinse or subject to these solutions. What would happen? So, remember the processes that we have. So we have crenation, not cremation. That's certainly a different process. Oh my goodness, come on. There we go. So crenation, and then hemolysis. I think it's actually pronounced hemolysis, but lysis means like your cells rupture. So which of those processes happen for these solutions? Tell me what you think in the chat. I'm going to number these 1 through 3. We'll go over the answers in about 2 minutes. One more minute, we'll go over the answer. All right, so we said a 0.9 solution for sodium chloride would be isotonic. This is more concentrated than that. And so what would end up happening here is that we would lose water from our cells by applying it. So this one would cause crenation, because water would flow out of our cells. For the second one, this is too dilute. Water would then flow into the cells, which would cause hemolysis. Or hemolysis. I don't know how to pronounce it. I've never actually looked it up. Now, for a glucose solution, 5% was our target. This is real close, so this is probably isotonic. You could also make the argument that you would slowly overhydrate, but odds are you'd be fine. The body is not that sensitive to water. All right, that's chapter 8. Let me know if you have any questions about it. I guess I could do this so you can hear the little hooray music. All right. Give me a second. We have 5 minutes. I guess I could just start this first section of chapter 9 here. Give me a second to get the slides. There we go. Okay. All right. We're sort of on the home stretch here. So what we're going to do is I actually am curious about something. Hold on, I'm just checking. Oh, it's in the middle there. Okay. What we're going to do is we're going to do the first section right now in like 5 minutes, because it's literally just, here are some reaction types. And we're going to talk about these 5 reaction types. So your task for the first part of chapter 9 is going to just be recognize what these reaction types are. And so the types are combination, where you combine things together; decomposition, where you break things into pieces; single and double replacement require you to swap one or two things; and then combustion reactions react with oxygen. And so these examples are just going to show you a bunch of these, and you can literally read through these because I have nothing else to really add. So, hey, I've combined things. Woo! Look at that. Here they are uncombined. Now they're combined. And then the opposite of that would be a decomposition. They were combined. Now they're not. So they fall apart. Sometimes the molecules are sort of hidden. So, for instance, calcium oxide plus CO2 makes CaCO3. One of the O's just hops over here. There you go. These are examples of very common decomposition reactions. Now, I should mention that the combination or decomposition may have some stoichiometry involved. So, in other words, these reactions right here, they very conveniently add together. But something like this is also a combination reaction. And then if I balanced it, it would look like this. So this would also be a combination reaction, because I combined two elements together. Single and double replacement require you... Oh, there's another one. there. Single and double replacement require you to swap out elements. In single replacement, one compound is getting replaced. So I swapped A and B, so I have the new compound AX, and my B is hanging out on its own. In double replacement, I have two compounds, and I'm swapping both of those. So here's an example of that. Here's a first compound. Here's the second one. I swap A and B, and I get two new compounds, as opposed to one new compound. So that's double replacement. And again, more examples of that. You can look at these slides later. And then the last thing to note is that combustion just requires oxygen. So if you have a reaction that has oxygen in it, it is a combustion reaction. So all you do is say, oh, there we go, combustion. And that's the first section of the chapter. So when you combust anything that contains only carbon, hydrogen, or carbon, hydrogen, oxygen, the products you get are always water and CO2. That's going to be relevant to us very briefly later on. But we'll come back to that when it's important. So I'm going to just put the homework practice for that section on the screen there, because that's very simple, and I don't think that that really requires me to spend more than 5 minutes on it. This is the sort of thing that you can just look up if you need to. You'll see reaction types on the quiz or the exam or whatever, and you just have to be able to categorize them into the correct category. So what would the first one be? Well, there's only one thing there, and then afterward there's two things. Must be a decomposition, right? And that sort of thing. So, all right, we're going to start the rest of Chapter 9 on Thursday. I'm going to try to do the best I can to either finish Chapter 9 or get really close. I'm going to put the quiz up for Chapter 8 tonight. And then I'm going to put the quiz up for Chapter 9 on Thursday. Okay, so there will be 2 quizzes next week, which I'll want to open. Actually, I'm going to have to make the quiz due date for Chapter 9 on Wednesday. Or it closes on Wednesday so that it will be open for you to see on Thursday. So you have it available for the exam. There is no quiz on Chapter 10. Exam number 2 covers that. So that's basically where we're at. Going to be 2 quizzes coming up next week. They might both be due the same night, so try not to let that pile up. Do one before the other. I do want to thank everybody for coming to the lecture. Let me know if you have any questions. We are almost done, so time is running out. If you have anything that you need from me, now's the time to do it. Oh, last thing to mention down at the bottom. So I'm going to send out an announcement for this tonight once I get everything set up. Course evaluations have opened, and they will be due by the end of the quarter. I do offer a small amount of extra credit based on the number of course evaluations I get. So if everybody that's enrolled in the class does the course evaluation, everybody gets some extra credit points, and that's always helpful, right? We like extra credit. That's all I got. Make sure to get quiz number 7 done tonight. It will close tomorrow. I'll get you all the other quiz stuff posted when I have some time tonight. Take care. See you tomorrow. See you Thursday.